Good morning, ladies and gentlemen. Myself, Mohammad Faisal Rahman Badal, lecturer, Department of Mechatronics Engineering, Russia University of Engineering and Technology. Along with me, we have Naimul Islam and Sharia Hussain as moderator to provide any sort of technical support to this session. Today, we are in the second day of 2021 International Conference on Automation, Control and Mechatronics for Industry 4.0. The current time is 10:40 AM Bangladesh Standard Time. I would like to welcome all of you in the invited session 02 of ACMI 2021. On this special occasion, we feel honored to have G.G. Muhammad Nawaz Ali, Assistant Professor, Department of Applied Computer Science, University of California, West Virginia, USA, as an invited speaker. ACMI 2021 has got a new dimension to have a resourceful person like him. So dear audience, this is the time to welcome our honorable invited speaker, this is Muhammad Nawaz Ali, with big round of applause. Thank you for your appreciation. It is our immense pleasure to have Professor Dr. Muhammad Raju Ahmed from Dhaka University of Engineering and Technology as chair, and Dr. Muhammad Tafiul Islam, associate professor from Independent University, Bangladesh, as co-chair of this invited session. After the end of the invited presentation, there will be a question and answer session. All the audience are requested to write question in the chat box. The audience can also raise hand in the Zoom after the end of the presentation. Now I would like to request our honorable chair and co-chair to take the floor and introduce our honorable invited speaker to the audience. Thank you, sir.
Thank you very much, MD Faisal Rahman. I am Professor Dr. Raju Ahmed. I'm working as Dean, Faculty of Electrical and Electronic Engineering, Dhaka University of Engineering and Technology, Duet, Gazipur. At the same time, I am the newly elected treasurer of IEEE Bangladesh section. It's my great opportunity to introduce the honorable invited speaker, GGMD Nawaz Ali. So I'd like to welcome you to the International Conference on Automation, Control and Mechatronics for Industry 4.0, ACMI 2021. We have Dr. M.D. Tafiul Islam, Independent University of Bangladesh, as a session co-chair in this session. So, honorable speaker, participants, and all of you, welcome all of you to the ACMI 2021. So, today our honorable invited speaker is MD Nawaz Ali, and his presentation title is Mobility for Tomorrow, Connected and Autonomous Vehicle Perspective. So he's very renowned in this field, and I saw his Google Scholar. So if you are interested, all of you are welcome to see his publications in the Google Scholar. I am very shortly speaking about our speaker, GJMD Nawaz Ali received his BSc degree in computer science and engineering from the Khulna University of Engineering and Technology, Kuwait, Bangladesh in 2006, and the PhD degree in computer science from the City University of Hong Kong in 2013 with the Outstanding Academic Performance Award. He is currently working as an assistant professor with the Department of Applied Computer Science of the University of Charleston, USA. Prior to joining this university, he was a postdoctorate fellow with the Department of Automotive Engineering, the Clemson University International Center for Automotive Research, USA, from March 2018 to July 2019. From October 2015 to March 2018, he was a postdoctoral research fellow with the School of Electrical and Electronic Engineering of Nanyang Technological University, NTU, Singapore. Dr. Nawaz's current research interest includes vehicular cyber physical system, data analytics, network coding, on-demand scheduling, data broadcasting, real-time scheduling, vehicular networks, software-defined vehicular networks, and mobile computing, and so many. So I already saw his profile. He is very potential, especially for this type of invited because the electric vehicles and the traditional vehicle system are now changing day by day. So I think he will give us a very details perspective of this research. So thank you very much, all of you. So now I like to invite JJ Nawaz Ali. Please take your floor and give your valuable speech. Thank you. Thank you very much.
Thank you, Dr. Raju Ahmed and Faisal and Dr. Kafil Islam. Thank you very much, and especially for inviting me and giving me the opportunity to share my research. And okay, let's share my screen first. Okay, let me see. Okay, I'm just sharing my PowerPoint. Okay. Can you see my screen?
Yes, yes.
Okay, that's good. Okay, so so today I'm going to talk about mobility for tomorrow, connected and artificial perspective. So basically, I'm going to focus two of my recent projects. One that we just recently finished with the collaboration of the Clemson University in South Carolina in USA. And then other one, I'm going to talk a little bit about the testbed deployment in Nanyang Technological University in Singapore. So I was postdoc in there. So yeah, although I mean, when I sent my biography, I said, okay, I'm working with the University of Charleston. So, but this fall, I'm moving to another university. I'm going to Bradley University in Illinois. So that will be the Department of Computer Science and Information Systems. So that's it, like, so that's the most updated one. So anyway, so I mean, until this spring, I was with the University of Charleston. So I got a better opportunity to do some more research, have some funding with the Bradley University. So anyway, without any further ado, let's get started. So so this is the first slide. Basically, it shows that what we are currently, according to the Society of Automotive Engineers Automation level. So we are talking about the vehicle, right? So it's like driverless vehicle. So you have totally, let me take the laser pointer. So there are like 6 levels in terms of autonomy. So the level 0, that means the vehicle is fully human-driven vehicle. So that's the driver will control the full vehicle. And level 5 means the full automation. So that means it's a fully driverless vehicle, and the vehicle can do all the maneuvering. And so right now, if you see that latest model vehicle, for example, Tesla or some GM, they're producing some vehicle which has like level 3 or level 2, some features, some partial automation. So for example, cruise control or lane keeping, that kind of thing. So anyway, so the project that I'm going to talk a little bit on the first part of my presentation is the connected and autonomous vehicle. So that means fully autonomous vehicle. Okay, so that's level 5 vehicle. Okay, so that's the project was funded by the US Department of Energy. So basically you can think about that because it is funded by Department of Energy. So although it's a CAV, that connected and autonomous vehicle, but it has the energy perspective of it. So that's the presentation outline. Basically, I'm going to talk 2 of my project. One is the connected and autonomous vehicle with the energy efficiency, and another one with the live test bed for the V2X communication. V2X means vehicle to everything communication. That's the project that was implemented in Singapore. So, and I was as a postdoc in that project. So let's focus on the recent project first, the CAB project. So the project title is Boosting Energy Efficiency of Heterogeneous Connected and Autonomous Vehicle Fleets via Anticipative and Cooperative Vehicle Guidance. So that means this is a heterogeneous CAV. So heterogeneous means that there will be some human-driven vehicle and there will be some autonomous vehicle, because in reality, you cannot assume that all the vehicles suddenly will be autonomous vehicles. So some vehicle will be human-driven, some vehicle will be autonomous. So so our project consider the heterogeneous traffic. So in this project, so basically there are mainly 3 tasks. First task is algorithm design. So in the algorithm design section, there is 3 things. One is the traffic perception and the prediction. So that means you need to know who are your neighbors. So for example, if you think that you are an autonomous vehicle, so what you need to know? You need to know your neighbors, right? And you also need to know that what is their behavior. So whether they're changing the lane or what is their speed, acceleration, that kind of things. Then other thing is about your own maneuvering thing. So for example, when you drive a vehicle, basically you need to do 2 things, right? One is the lane keeping, or keeping the safety distance, right? So that is car following distance. So what should be your car following distance? The another one is lane selection. So that means if you want to change the lane, then you need to see that whether there is another vehicle in that lane, and what is the speed of the following vehicle. So if that vehicle is on the same lane. So that's the 3 important part for when you want to design an autonomous vehicle. So that's the task 1. Second task of this project was the simulation, creating the simulation environment. So because, creating an autonomous vehicle or buying an autonomous vehicle is very, very expensive. So what we have done in this project, so we basically have 2 autonomous vehicles, and then we have created 100 of simulated vehicles. So simulated vehicles we created using the microsimulator PTV vSim. So some vehicle are human-driven simulated vehicle, and some vehicle are autonomous vehicle. Okay, and then there is some energy part that was done by another company, the Argoni Lab, which is the collaboration of the German company. And then the task 3 was the real world implementation. Okay, so that means we have basically, if you want to buy autonomous vehicle, is very, very expensive, and our project did not have that much money. The project was just like, I guess, $1.5 million project. So we did not have the luxury to buy the fully autonomous vehicle. So what we have done, we bought 2 normal vehicles. One is the Nissan Leaf and another one is the Mazda. And then we have retrofitted that normal vehicle to the autonomous vehicle. Okay, and then we have done some testing in it's called ITIC test in Greenville, South Carolina. And then we have analyzed the energy efficiency. So basically the energy efficiency part is what will be the energy saving. So here the energy savings mean the fuel consumption saving. Okay, so how much fuel you can reduce when at a certain penetration of the autonomous vehicle are on the road. Okay, so basically it actually save, because the autonomous vehicle have the information that when there will be the green light, when there will be red light, and so it has the beforehand information, so um, it can do its acceleration and speed control. And so if there is a certain penetration of autonomous vehicles, so the following vehicle, if it is a human driven vehicle, they also get some advantage in terms of fuel saving. So in terms of fuel, basically why the vehicle has I mean need more fuel is basically the braking event. If you have more braking event, then there will be more fuel consumption. So but the autonomous vehicle does not need to do a lot of braking, but they can save a lot of full savings. Anyway, so I'm not going to talk about lot of that part. Basically, I'm from computer science, and my research is the wireless communication domain. So I'm going to focus on my part, what I have done in this project. And so I'll focus on that. So the expected project outcome for this project is to save at most 10% energy gain with the certain penetration of autonomous vehicle on the road. So this is our first autonomous vehicles. You can see this is a Nissan Leaf. It has the DSRC and Wi-Fi connection for communicating with the other vehicles or the roadside infrastructure. It has a wheel, the robot steering wheel, so the vehicle can drive itself. And this is the ITIC test track. And so um, this is the vehicle in the loop simulation. So we did the vehicle in the loop simulation because, as I mentioned, that it is not possible to create 100 of autonomous vehicle physically, because it's just simply is too much expensive. So what we have done vehicle in the loop simulation. So this is that the black vehicles are the simulated vehicles, and then this orange vehicle is a real vehicle. So basically the real vehicle can get the information on the real time, this preceding vehicle and the following vehicle. So that means this is kind of ghost vehicle. So physically they're not there, but the autonomous vehicle can get this information. Okay, there are some vehicles. So he needs to change his maneuvering decision accordingly. Okay, so this is the vehicle in the loop simulation concept. So the autonomous vehicle, it will send its state. Okay, so state means what is its current position, and speed, acceleration, heading information through the heterogeneous networks. So the heterogeneous networks means there are the DSRC communication, dedicated short range communications, Wi-Fi, LTE, 5G network. So that's a head net. And through the head net, it will send its state to the server, the simulation server, where we implement the vehicle in the loop simulation. Okay, so in here, using the PTV vSim, we'll generate 100 of simulated vehicles, and we'll do the vehicle in the loop simulation. And then send all the state of all the vehicles, send back to this real vehicle, and then real vehicle then he needs to make his own maneuver. Okay, so he know that there are some other vehicles, although they are like the ghost vehicle. They're not really in there, but their abstract positions are there. Okay, so let's focus on the integrated simulators. So how the simulator was implemented. So the simulator has like PTB vsim. So PTB vsim basically used to create the simulated vehicles, and then there is NS3, the network simulation. So network simulation is basically where you can implement the layers, like the physical layer and the math layer implementation. And you can also collect like performance metrics, like the packet delivery ratio or that kind of things. And then you have the MATLAB also. So MATLAB works as a client, and the NS3 run in a server machine. So basically MATLAB, what it will do, it will invoke the PTB vsim. So that's for initiate the PTB vsim. And then via MATLAB, so PTB vsim NS3 will work. So why we needed the MATLAB is because the PTB vsim only works on the Windows. It does not work in the Linux machine. But the NS3, other hand, run in the Linux machine. So we have like this kind of, oh my God, so just give me a second. Alexa, turn on light 2. Alexa, turn on light 1. Okay, sorry. I mean, there was my schedule. So it's like 1 a.m. morning. So my the schedule that okay that time will be goes off. So anyway, so so that's the integrated simulator. So in the next slide, we can see that how this simulator works. So basically, this is the NS3 is running in a Linux machine. So NS3 implemented in C++ code. I don't know whether you're familiar with the Network Simulator 3. Is use the waypoint mobility model. So and then so now it is running. So this is basically the server. And then now waiting for the client. So client was implemented in the MATLAB in the Windows machine. So in here is basically you can set how many vehicles, simulated vehicles you want to generate, what will be their state, what will be their speed, and what will be their position. And then it also invoking the PTB vsim. So PTB vsim, as I mentioned, is a microscopic traffic simulator where you can design the road, you can create the vehicle. So for example, this is the road, like 1.5 kilometer stretched road in the Clemson University International Center for Automotive Research area. So the vehicle is now sending its status that whether it received the packet or not. So this is now the NS3. From the NS3, you are getting some output. So like the packet delivery ratio, latency, and throughput, that kind of things. So that's basically in a nutshell how this integrated simulator works. So it has like 3 components. One is the NS3, the network for doing the network simulation, PTV for generating the road network. And so you can generate the road in anywhere if you have the OpenStreetMap. And the MATLAB is basically works to invoke the PTV and send the initial information to the PTV. So, and then they will work PTV sim and the NS3 in the real-time situation. Okay, so this is the simulation in the network NetAnim simulator, network animator. It shows that we have 50-meter communication range and how this DSRC protocol is working. So DSRC is called dedicated short range communication. So you can see that each vehicle is basically, it's a very strict protocol. So only one time one vehicle is allowed to send the packet, and then other will sense the channel. And whenever they get chance, then they will broadcast their packet. So basically, this is the basic safety message. The vehicles are and this one is the NetNM simulator when you have the 300-meter communication range. So that means now the more vehicles are within your communication range. So maybe the more vehicle can receive your packet. But there is another issue when you have the bigger transmission range. There is some hidden problems and then packet collision problem as well. So we'll see in the next slide that so what is the performance when you increase the communication range? So before that is basically one thing we need to implement about the path loss modeling. So the path loss modeling is, so consider here the vehicle V1 in the intersection situations where the vehicle V1 and V2 are blocked by a building. So assume this one is a building, this one is a building. So they're blocked by a building. So basically they don't have direct line of sight communications, but vehicle V1 and V3, they have the direct line of sight communications. So LOS communications. And vehicle V1 to V4, they have obstructed line of sight communication because there is a big commercial vehicles is there. Okay. And so although for the same transmitting vehicle, based on the position of the different receiver vehicle, you will have different types of communication pathways. Okay. So we have developed an algorithm to realize that path loss. Okay. So basically, when if there is a whether there's a line of sight communication or obstructed line of sight communication is really depends on the distance. Okay, and then probability of being a loss line of sight communication or probability of being obstructed line of sight communication. So the equation for path loss and for line of sight and obstructed line of sight, it's not in here. It's basically you can find in here. So this is published in IEEE Transaction on Vehicular Technology Journal. So the another important thing about the obstacle shadowing. So obstacle shadowing means if there is a building between the transmitter and the receiver vehicle, okay, so how much signal will be attenuated, okay, so that will be computed using this equation. So where M is the number of walls that the signal will penetrate, and then dm is the distance that through the building or through the garage the signal will penetrate. Okay, and alpha and beta are some tuning parameters based on the types of the buildings and the materials of the buildings. Okay, and then so you implement you will compute this path loss due to the obstacle shadowing, and then you will compute the receive power. So receive power of a packet. So that's you know what is the transmit power, at what transmit power you are sending the packet, what is the antenna gain, and then you subtract all the losses. So loss due to the line of sight or obstructed line of sight communication, which is basically heavily depends on the distance, and then loss due to the shadowing, if there is any shadowing, then you know the receive power. So when you know the receive power and you know the receiver sensitivity, and then you can decide whether the packet is received or not, okay, or is just packet become a noise signal. Okay, so we have implemented that one with our simulator, and so this is the networks that I have shown in my previous slide. So it's like 1.5 kilometer stress ACMI road network, which we have like one roundabout and two traffic light intersection and two priority intersection. And then on top of this, we also have proposed a feedback-less relaying mechanism. So the feedback-less relaying mechanism basically will Okay, let me show the next slide why we need the feedback-based relaying mechanism. Is basically consider the situation vehicle V1 and V4, their signal are blocked by this building, okay? But if you have an opportunistic vehicle like V5 here, then he can work as a relay vehicle, okay? So the vehicle V1, when it broadcasts its packet, vehicle V5 can receive, and then he can relay that information to V4. Similarly, V4 information also can be relayed back to V1, okay? So how this vehicle will be selected, okay? Or for example, in here, say V3 and V4, they cannot communicate if, for example, because of V2. But assume that V2 is a big vehicle, big commercial vehicle, truck. So that then you'll be high signal attenuation, okay? But V2 can be a relay vehicle, and then V1 and V3 can communicate. So anyway, so we have proposed a feedback-based relaying mechanism to improve the performance, the communication performance. And that has been published also in another IEEE transaction on vehicular technology paper. So I'm just showing like one result from that paper, but I mean, if you want, you can definitely go and check if you're interested. So the improvement was 35% in our proposed feedback-based relaying mechanism. So these two curves is basically when you have the line of sight, obstructed line of sight, and non-line of sight combination path loss model you selected. And this one is when you have no relaying mechanism. And this line is basically when you have the relaying mechanism, and then what is the packet delivery ratio. Okay, and these two lines when you consider the freeze neck-agamic path loss model, and this one is when you do not have relaying, and this one is when you have the relaying. And it is changing for the transmission receiver communication range. So that means when your transmission receiver communication range increase, so the signal has the higher attenuation, and there will be more fading. So that means the signal strength will be lower. So that's why you have the lower packet delivery ratio when you increase the distance. Now, the another concern was the latency. So what is the latency when you do the relaying? I mean, basically, because when you do the relaying, definitely there will be some latency, right, increase, because the relay vehicle will receive the packet, and then you will check the packet and then forward, right? So we have seen that when you do the relay, then it has the higher latency than without relaying protocol for the receive packet cases. But that latency is not too much. It's only 10 millisecond time. So that means it's a tolerable latency, because for the safety applications, you can tolerate at least 100 milliseconds. So basically, the vehicle generate the packet every 100 millisecond interval. So that means the 10 millisecond is tolerable latency. Although it increased a bit, but it's tolerable. The another thing we analyze about the expected per packet latency. So that means when you consider both the receive packet and the drop packet. Okay, so drop packet basically contribute more latency because when a packet is dropped, so that means 100 millisecond is gone. So then you generate another packet, right? So when you consider both the receive packet and the drop packet, we see that without relaying has a more expected per packet latency. Okay, it's understandable because the drop packet contribute more than the receive packet latency, because when you receive the packet, it's definitely coming within 100 millisecond. But when this packet is dropping, that means your 100 millisecond is gone, and you no longer wait for that packet. Okay, so this is the another paper which is also been published in IEEE transaction on vehicular technology. So here basically we focus on the network coding implementation for the application level network level reliability. So the Application level reliability means, okay, so what is the network level reliability and application level reliability? So the network level reliability is basically in a packet delivery ratio. So how many packets you send, how many you receive. Okay, that's the competition for the network level reliability. The application level reliability means that what the driver is experiencing. Okay, so that means if you don't receive one packet, maybe that will not harm you for making your decision, maneuvering decision. But if you lose consecutive packet from the same sender, then it will harm you for making your maneuvering decision, either lane keeping or lane changing decision, right? So that's also important, okay? So here, the T window means delay tolerance. Okay, so some applications. So basically, these are a couple of applications. So T window 300 millisecond means it's a very delay sensitive application. So for example, lane changing applications or emergency braking light applications, um, or the delay tolerant application is like, for example, stop vehicle warning application. Okay. So in the delay sensitive applications, so this is the curve that what is the application level reliability when you do not use the network coding relaying. Okay. And it shows that when the distance between the transmitter and the receiver is 150 meter, your tuned reliability is only 70%. With the existing DSRC technology. So which is not enough, because that means 30% of the time a driver may have a problem to make a decision. Okay, so we have improved that in this paper by proposing network coding based relaying protocol. Okay, and it shows that even for delay sensitive applications, for example, T equal to 300 milliseconds, our reliability is almost 90%. And when you have the T window is 1 second time, so if it is a delay tolerant applications, for example, stop vehicle warning, then your reliability is almost 100%. Okay, so definitely there is a significant improvement from the existing technology. Okay, so now I'm gonna focus on a little bit about the hardware part implementation of this project. So this is the concept diagram how the network was created. So this is the vehicle. Vehicle has a moderative control algorithm for its maneuvering decision, and this is the DSRC radio. So this one periodically sends state information, and then the roadside unit will receive that packet and send to this server machine. It will do the vehicle in the loop simulation, send back this information again to this vehicle, and then vehicle will make or update its maneuvering decision. So that's the idea has been implemented. And for that, we use the DSRC hardware in the DSRC protocol. So this is the test environment when we are checking before going to the test bed. So we use, so for the upper layer implementation, we use IEEE 1609.1.2.4, and the lower layer implementation, we use IEEE 02.11p for physical and MAC layer implementation. So here it shows that how the transmitter and receiver communicate. So basically receiver is ready to receive the packet, and then transmitting vehicle is now sending packet, as basically sending is latitude, longitude information, and then speed information, and then receiver vehicle is receiving that. So now I'm going to stop this transmitter, and then receiver won't receive anything. So this is a small setup in my on my desk, my office, and so how this communication is done. So now I know that's how much time I have. I have probably a couple of minutes because we have started late, like 10 minutes. So I'm gonna finish very quickly. Give me like 5 to 7 minutes. So this is the next, I mean, not the next project, it was the previous projects that's I have done with the Department of, School of Electrical Engineering in Nanyang Technological University in Singapore. So that was basically the test bed deployment. So in that test bed, the V2X communication, vehicle to everything communication, we have done a lot of use cases, like intersection collision warning, so extended cruise control, and then forward collision warning, that kind of things. And it is implemented in a big campus. Although Singapore is a small country, but they have a two big university, NTU and NUS. So this campus was like a, and we have covered the whole campus with the roadside unit. I don't know whether you can see it. There's a red circle here. So each red circle represents the communication range of a roadside unit. So we have installed 50 roadside units, the whole campus. We had the 100 vehicles fitted with the onboard unit for testing purpose. And so this is the test-based infrastructure. So we have over 100 plus IP video cameras so that you can see how the traffic is moving inside the campus. So we have the video surveillance system, data centers, which collect the data, analyze the data, and then wireless and data transport networks. We have our, is a mixed clutter environment. There is a tall building, there's a weird type of building. So it's a very good area to see that how the V2X network works. So we have different kinds of vehicles like bus, the campus shuttle bus, cars, motorcycles as well. The software, we have our own software and app services, and then command and control center, which you can see in here. So it's like 3,000 square feet laboratory space. You have a big giant wall screen where you can see that whole campus network, because we have over 100 plus video camera to live see the traffic. And then you can also dispatch some information if you want to send that information to the vehicle, or if there is anything happen, like accident kind of things happen, you can send that information to the law enforcement agency and they can do their job. Okay, so on the top of that test bed, we had 7 research projects. There's a lot of research have been done, a lot of paper have been published in this project. So I work in this project, network coding for network load reduction. There are some other projects. So basically we have touched all the layers and implementing, say for example, antenna, we have developed that antenna. We have also implement the physical layer, the massive MIMO. We do the network coding, we do the security and PKI algorithm design. So yeah, so that's the project in a nutshell. So now this is the major V2X wireless equipment that we have used for the test bed. So this is the onboard unit that will be on the vehicle, the roadside unit that will be on the lamppost, and mesh router that will connect the REC with the campus backbone network. And this is the overall V2X network architecture. So each vehicle connected with the onboard unit, and then you have the roadside unit on the lamp pole. So the vehicle can communicate with the roadside unit. And then there is a mesh router that will connect this RSU information to the campus backbone network. Okay. And then that will bring to the data center, command and control center. So that's like whole architecture of the network. Now this is the some snapshot while we do the installation on the vehicle. So this is the antenna on the top for the onboard unit, and this is the OVU inside the vehicle. So this is just like plug and play. So you can just so there is a magnet down there, so you don't need to attach with anything. You just put the antenna on there and it will be mounted easily, and then you just plug the onboard unit and then it will be a connected vehicle. So this is our first roadside unit, and then this is the mesh router. This is the vehicle. This is the demo vehicle. So every 6 months we have showcases our project outcome to our industry partners and Singapore governments, agencies, and common people to see that how the V2X network works. Then this is one of the use cases. So emergency vehicle alert relaying, EVA relaying. So for example, this is a campus security vehicle um, or the ambulance is coming and say this is a passenger vehicle. So assume that these are on the same lane. And you can see there is a car park here, and there is also a road curvature. So normal DSRC technology, through that, this vehicle cannot reach the information. Okay, there is a emergency vehicle is coming, but we have set a dummy vehicle here, and that will actually forward, relay his information, EVA alert, to this vehicle. And then the vehicle will know, okay, there is emergency vehicle is coming. So change the lane or take a side, and then this vehicle will pass. So this is the use cases implemented from our project in that test bed. And this one actually shows that how in the lab environment it was working. Okay, so when the emergency vehicle is coming, and the passenger vehicle inside the same communication range, so it will receive the information, EV alert. But if the passenger vehicle is far, the relay vehicle will help to relay that message. Okay. But if you have broadcast 2 times, a relay vehicle send the same message and the passenger vehicle also itself receive it. But this protocol also can detect, okay, the packet, whether the packet is duplicate packet or the original AVA message. So in the SMTP technology, we have implemented a lot of technology, like network coding, mapping, video analytics, data analytics, cloud computing, cloud infrastructure, locationing, vehicle tracking, you name it, platooning. So lots of research have been done under this project. So there are some use cases video, but I'm not going to play right now because we're running out of time. But you can search, if you search that SMTP videos use cases in YouTube, you should be able to see that videos. So quickly, I'm going to wrap up with what my ongoing research direction is. So far I have shown you some research on the DSRC technology, but we are also working with the LTE V2V technology, which is called C-V2X technology. So now cellular company, they are also working for this vehicle to vehicle communication and vehicle to everything communication, V2X communication. So we have also done some work that also has been published recently in IEEE transaction vehicular technology. The another works that we have done to extend the field of view of an ego vehicle using a filtering model and sensor perception, and using the V2V communications. And then we use data association and data fusion. So that means from the different sources, you get the perception for the same objects. And then this protocol basically will fuse that information and give a more accurate information to the autonomous vehicle for its make its maneuvering decision. And this one is published in this year in IEEE Transaction on Intelligent Transportation System journal. The another recent work that we have done with the hierarchical traffic control using distributed fog computing network, where the whole network is divided by a couple of sub-network controller, where each sub-network has type 1 controller and type 2 controller. The type 1 controller control the link road, and then type 2 controller control the intersection. And then they have a communication with the traffic control center, TOC, so which has the better view of the whole traffic. So he can make some informed decision and send this information as a guidelines to this vehicle. I know that I'm running out of time. I'm gonna wrap up very quickly. So this is my relevant research paper, a recent one. And there are some possible student project from my research, but I'm running out of time, I know, so I'm gonna finish it in the next slide. So that's it. And yeah, we can take some questions. Thank you.
Thank you very much, dear MD Nawaz Ali, for a very nice and informative presentation. So we have a very rich project experience. So that's actually very necessary for this type of talk. So thank you very much. Now the floor is open for question and answer. So I like to take a very short question. If you have any question, please raise your hand, or you can make directly to our speaker. One question in the chat box. AK Niloy, he want to actually know, did you take any cyber security measure for the vehicular networks? Or what type of cyber security measures you have considered for vehicular networks?
Okay, so yeah, I mean that's a very hot and important research domain in that V2X networks. But yeah, I mean, I probably in one slides I shown that that there is a project on the security and the public key encryption, and so yeah, so there are some another group in our project. They have done that one, but I was not in that project. So my expertise is especially algorithm design and the wireless communication part. So yeah, I didn't do the security algorithm development, but there are some other groups, they have done it.
Thank you very much. So if you have any question, please raise your hand.
Yes, I have one question for Dr. Ali. First of all, thank you, Dr. Ali, for the nice presentation, very informative and exciting research, as autonomous vehicle seems to be the future. So I would like to know what is the performance metrics to actually evaluate the safety of an autonomous vehicle, which is a big concern.
Yeah, so basically, you know, definitely safety is the first thing, and the autonomous. So the consideration of the autonomous vehicle is basically how to improve the safety. So the safety, the obvious metrics is the fatalities and the accidents. So whether you have less accident, so according to US National Highway Traffic Safety Administration, every year more than 30,000 people die due to the car accident. And there are crashes, a lot of crashes happens. So 30,000, more than 30,000 die, but you can imagine how many crash happens, because in here they like to drive the vehicles. So, and that's just very common. So yeah, so the metrics is whether you have less crash, okay, less accidents, less death, okay. So that's the reason. And main reason actually, according to the US DOT, Department of Transportation, the main reason it's not about the mechanical failure, especially in this country. The accident is main reason in the unattentive driver. Maybe the driver is sleeping, or he was too tired, or you know, the driver was a younger boy or girl. There's a hormone issue. There's so many things. So the main reason is the unattentive driver. So that's the main driving force to go to the autonomous vehicle, so that you can reduce the number of collisions, number of accidents.
Thank you very much for your nice answer. So if you have any question, any participant. So actually, one of the important issues to move towards the autonomous vehicles is the energy saving, very demanding issue, challenging issue for energy saving. So in case of autonomous vehicle, you have already mentioned that number of brake required is less than for man driving vehicle. So is there any other region for improve the energy saving? only the braking reduction of braking is the reason, or for any other reason?
So there are a couple of reasons. Definitely, that's not the only one reason. That's the main reason. Now, so for example, when you drive the same vehicle in the city or in the highway, you can see, for example, I drive my Toyota Camry. MPG, mile per gallon, is in the city area is only around 22, okay, 22 mile with the 1 gallon I can drive, or 18, sometimes even 18, because when you have traffic, you need to brake a lot. But when in the freeway or the highway, where there is no traffic signal, you just drive smoothly, okay? And that is around 33 mile per gallon. So, I mean, that's definitely the braking is the main reason, but there are some other reason as well, right? For example, the engine quality, whether you are using AC, air conditioning in the car or not. But the main reason is the braking event. If you have less braking event, you will have less energy consumption.
Okay, thank you very much. Another issue is huge. In my concern is huge investment will be required for this type of network, this type of vehicles. So it may be possible for a developed country to incorporate this type of technology or vehicles very soon. But what about the country of third world or like developing country? So I think it will be a very challenging issue for them.
Yeah, I mean, for the autonomous vehicle, so the another driving. So one thing I told that the reason the autonomous vehicle is safety, because there are more crashes, more accident, because when the driver is a human, there is a human error factor. But the other important driving force towards the autonomous vehicle is so not all the people has their own vehicle. Not all the people has their driving license. So when you'll have the autonomous vehicle, so the vehicle will be shared. Okay, so that's the another concept. So you don't need to be a driver. You don't need to be you should not need to have a driving license. You just go sit on board on the vehicle and just press the button. Okay, I want to go, this is my destination. I want to go to Ruwait. Right now I am in somewhere else, like 5 miles away. Just press the button and the vehicle will take you, drop you there, and then that vehicle will serve to another customer. So that means that is the sharing concept comes. So that's probably the another important factor that will be for the developing country, where you cannot imagine all the people have their own vehicle. But it's also not possible because the road infrastructure is not built in that way. If you have all the people have their own vehicle, you see the situation in Dhaka, and there's a traffic jam. But when your vehicle will be shared, there will be, you need less number of vehicles than dedicated vehicle for each